class. It's lecture 13 of the course. We're discussing electricity. To get things started, we're going to first talk about a fundamental concept behind electricity, and that is the concept of charge. So electric charge is a property of matter that if a particle has charge, that means it will exert a force on any other matter that has charge. And the direction and the strength of that force depend on different factors. But there are, in nature, there are two types of charges. There are both negative charge and positive charge. So there's negative and positive charge. And these charges ultimately arise from two particles. We have the negative charge is from electrons, and positive charge are from protons. Now, in an atom, if you're familiar, there's electrons, protons, and a third particle, neutrons. The protons and the neutrons are in the nucleus, the electrons are outside the nucleus. Neutrons have a neutral charge. Doesn't mean that there is no charge. In a neutron, it means that there is the same amount of positive as negative charge, so that they cancel each other out. There is positive and negative charge, and if you put positive equal amounts positive and equal amounts negative charge together, they have a canceling effect in the case of neutrons. So that's what charge is, right? And since matter is composed of atoms that have protons and electrons in those atoms, the relative abundance of protons and electrons determines the net electrical charge of an object, of matter. So if there's more electrons than protons, then it's going to say to be negatively charged, as it has an excess of negative charge. If there are fewer electrons than protons, then it's said to be positively charged, as in there's more positive charge than negative charge, there's more protons than electrons. So that's how an object develops a net charge, is by having an imbalance of protons and electrons. And that the negative charge of one electron is the same amount of charge as the positive charge of a proton. So they have the same amount of charge, an electron and a proton, just different types of charge. Electrons we call negative, protons we call positive. So that is the fundamental concept of charge, and that is electricity, right? Electricity is basically the idea of charge and flowing charge and net charge and the forces that charges exert on each other. And so charge, just because you cannot change the amount of matter, the electrons, number of protons, and the number of electrons that are present, the total charge also has to be conserved. You can't just make charge appear or make charge disappear. That would be making protons appear or disappear, or making electrons appear or disappear. You can't do that. So for that reason, charge must be conserved too. And we'll talk about that in a second. So let's say we have an object, going back to charge for a second, and it has no net electrical charge. We say it's neutrally charged. So it has positive and negative charges mixed in. So it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There's the same amount of negative charge as positive charge, okay? Now it's electrically neutral. Now if we somehow can pull off, so whenever we charge an object, say if we rub a balloon on our hair, or rub some wool on a piece of glass or something, what we're doing is we're scraping off electrons. And by scraping electrons off of one object or one material, you're removing negative charge, so thus leaving that material positively charged, and the electrons are going to the other, so there's an excess of negative charge, so that object is negatively charged. But fundamentally, we did not change the amount of overall charge, we just transferred charge from one object to another. So you can have two objects that are neutrally charged. They have the same number of protons as electrons, both of them. And you rub them together, and you can transfer electrons from one object to another. The object that lost electrons is now positively charged with more protons than electrons, and the other object is now negatively charged with more electrons and protons. So let's say that with regarding charges, if you have a negative charge, the force that it will exert on another charge depends on what type of charge it is. So if we look at a positive charge, these are opposite charges, and so they will result in an attractive force. So opposite charges attract each other. And so per Newton's third law, that every force has an equal and opposite force, if the attractive forces these two charges exert on each other are equal in magnitude or strength, but opposite in direction. So opposite charges attract, where if it was a negative charge and a negative charge, they would repel, and a positive charge and a positive charge repel. So like charges repel. So the force, the direction of the force that charges exert on each other is determined by the type of charges involved. Like charges repel each other, negative repel negative, positive repel positive. Opposite charges, positive and negative, attract. Okay. So let's say we have a neutrally charged object, and if we bring so this electrically should not attract anything, any other charged object. But if we bring a negatively charged object close to it, what's going to happen is the negative charge of this object is going to attract the positive charge of the neutral object and repel the negative charge of the neutral object. And so what will happen is the negative charge will collect on this side, and the positive charge will collect on this side. And so now, because these positive charges are over here, they're going to be attracted to these negative charges, so that's why they move over there, and these two objects will experience an attractive force. So that's an important thing to understand, is that if you have one charged object and bring it in close contact with a neutral object, the charged object can attract a neutral object. How it does that is the charge of the charged object separates the charge of the neutral object, and that the opposite charge aggregates on the side closest to the charged object, and that creates an attractive force. You ask the question, well, aren't these like charges repelling? Aren't they being repelled? So wouldn't the repulsive force between these negative charges and these negative charges cancel out the attractive force between these positive and these negative? Well, as we'll learn, the electrical force is very sensitive to distance, and it decreases with distance very rapidly. So because these positive charges are closer than these negative charges, the attractive force between these negative charges and these positive charges is stronger than the repulsive force between these negative charges and these negative charges, being that they're further away. And so the net force, electrical force, is going to be this way on this neutral object, because it's still electrically neutral, right? Because there's still the same amount of positive and negative, but the net force is going to be this way because the attractive force with these positive charges is slightly stronger because it's slightly closer. So if you bring two objects together and they, if one object for sure is charged, and they're going to attract each other, then one of two things could either be the case. Either A, the other object has the opposite charge, or B, the other object is neutral and there's an induced charge or attraction. Okay, so if there's an attraction between two objects, they either A, have the opposite charge, or B, one of the objects is neutrally charged. That's how, if you charge a balloon, it's how it sticks to the wall. Right? The balloon induces a charge in that part of the wall, and it sticks to those charges. The wall is electrically neutral. And then if you have a charged object and bring it next to another object and they push each other away, then the only way that can happen is if both objects are charged and they have the same charge. Okay? So if there's attraction between objects, either A, they have the opposite charge, or both charged and have the opposite charge, or B, one's charged and the other is neutral. But if they repel each other, then they both have to be charged with the same charge, both positive, both negative. So what types of materials can hold a charge and transmit a charge? Well, there's different types of materials, and they basically have to be able to have free electrons. Electrons have to be able to free, to either be added or removed, and move through the material. So any material in which electrons can move freely within the material, it can hold and conduct a charge. And those are called conductors. And there's many different types of conductors. Metal is a very common conductor. Water is a conductor. And so because water is a conductor, and your body is mostly water, your body is a conductor. The earth is a conductor. There's a lot of different materials that are conductors. And then the opposite is an insulator. An insulator is a material that doesn't have free electrons. So it cannot hold a charge, and charge cannot pass through it. Plastics are a good example of an insulator. So that's why a lot of electrical wiring, copper wiring, the copper is the metal, it has a plastic insulator wrapped around it to protect from electrical shock, because the electricity cannot conduct through the plastic. All right? So if we want something like a metal ball to hold a charge, we have to put it on something plastic. So this would be a conductor, this would be an insulator. Because if this was connected to anything else that is conductive, its charge, say if this is a negatively charged, its charge would be spread out. Okay, it would be spread out. So say if this is the earth, if this metal ball is on a plastic pedestal, it can hold a charge because it's insulated from the earth. But if we would touch a wire to the earth and then just touch that wire to the ball, what happens is this neutralizes. This excess negative charge flows to the earth, right? And it'll become neutral. Well, the same number of protons as electrons become electrically neutral. And that's called grounding. Okay, when we ground something, that means we connect a conductor to something that the electricity can flow to, so that conductor will not develop an excess charge. It will stay electrically neutral. So a conductor can develop an induced charge as long as it can develop a net charge as long as it's not grounded. All right, so but if it's grounded, it will never develop a net charge, positive or negative, because it's always connected to another conductor, a large conductor like the Earth. Okay. So those are insulators and conductors, and what grounding is. This conservation of charge. Let's say you have a negatively charged object, right? And it has a certain amount of charge, and this is neutrally charged. And you put them in contact, what happens is these charges, these are like charges, there's an excess of negative charge in here. They repel each other, they're going to want to spread out. And so if you put them in contact, The charge says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The charge will spread out. So this had a certain amount of charge, negative charge. This had no charge, it was neutral. Now, each object will have half of the charge the original object had. However, the total charge is the same. Conversely, let's say this had a positive charge, 2, 3, 4, 5, 6, 7, 8, 9. Had 10 charge, so they had the same charge, but the opposite charge. This was negatively charged, this is positively charged. If they touch together, the charge would redistribute so that there is equal amount of charge on both ones, and the total charge would be, net charge would be 0. So they would become neutral, so they kind of had this negating effect. So instead of net negative charge and net positive charge, the same amount of charge, we put them together and the net charge is now 0. They cancel each other out. But still, the total amount of charge is still there. It's just that there's an equal amount of negative charge and positive charge present, so it's neutrally charged. Okay? So whenever something is neutrally charged, I just want to stress, that doesn't mean that there is no charge present. It just means that there's the same amount of negative as positive charge. Okay? So that's the conservation of charge. Charge didn't disappear. Even though this is neutrally charged, the charge didn't disappear. The charge is still there, it's just spread out now. Instead of being concentrated, negative concentrated here, positive concentrated here. Now, in reality, what's moving is the negative charge, the electrons. The electrons are the ones that are free to move. And so when these come in contact, half of these electrons flow to here. And so the electrons flow. But the convention, and this dates back to whenever Benjamin Franklin was studying electricity, the convention is that we look at the flow of positive charge, which is confusing. But in reality, physically what's happening is electrons moving. So whenever charge is moving, it is actual negative charge. So that's the conservation of charge. So I want to talk about the electric force. Well, hold on. We'll talk about an electroscope quick. So electroscope is a rudimentary way of measuring charge. So you have some sort of beaker, you have an insulating stopper, you have a conducting piece of metal on a conducting rod, and then attached to it are two pieces of thin foil. Now, if it's neutral, electrically neutral, there's no attractive or repulsive force. So pieces of foil just rest alongside each other. However, if we charge this, say if we give it a negative charge, that negative charge will distribute, and those negative charges will be on the two pieces of foil, and so they'll repel each other. That negative charge will repel each other, so the foil will spread apart. And the amount of charge, net charge in the conductor, in the metal, will determine the strength of the repulsive force and how far those pieces of foil spread apart. The same thing would happen if it was positive charge. If this was charged with a positive charge, the same thing would happen because it's like charges that repel. And now, say if you have a charged electroscope, and if it was an unknown charge, say that we know this is negatively charged. Let's say we didn't know that. We wanted to know the charge of. Actually, let's say we know the charge. This is negatively charged. And say we had an object and we wanted to know what its charge was. If it was charged at all. If it was neutral, we bring it near the head of the electroscope, nothing would happen. Okay? If it was neutral. However, let's say if this has a positive charge. if we bring this near the electroscope, what's going to happen is this is going to pull, it's going to attract negative charge. So negative charge, this excess negative charge is going to be pulled towards the top. And so there's going to be less excess negative charge here, and so there will be a weaker repulsive force, and so these pieces of foil will get closer together. So if you have a negatively charged electroscope, and if you bring in a positive charge, the pieces of foil will fall closer together. However, if this was a negative charge object, this would repel the negative charge here, push more of the negative charge down into here, so there'd be more excess negative charge in the pieces of foil, and that'd push them apart even further. So if you have a negatively charged electroscope, and if you bring a negatively charged object near it, the pieces of foil will spread out. So with a charged electroscope, if you know the charge of the electroscope, you can tell the charge of a charged object by bringing it near the electroscope. If it's the same charge, the pieces of foil will get wider. If it's the opposite charge, the pieces of foil will get narrower, because you're sucking. It depends on whether the charge is pushed further down into the foil or pulled up out of the foil. And that's, if it's the same charge, more charge is pushed down here. If it's the opposite charge, more charge is pulled up there. So you can use electroscope, a charged electroscope, to determine the charge of another object. All right. So how do we quantify this electric force? Well, physicist named Coulomb figured this out, what the electric force is, and it's very similar to the gravitational force. So we know the force through gravity is equal to the gravitational constant times the mass of object 1 times the mass of object 2 divided by the distance between their centers squared. Right? And so the force due to gravity follows this inverse square law, where it decreases with 1 over the distance squared. So if you double the distance, the force is reduced by 1/4. If you triple the distance, the force is reduced by 1/9. If you quadruple the distance, the force is reduced by 1/16. So if you increase that distance, the force, the gravitational force, which is always an attractive force, decreases very rapidly. Also, the gravitational force is proportional to the masses involved. Well, the electric force is very similar, where it has to do with the amount of charge present. Little q is what we use to represent like a test charge or amount of charge, divided by the distance between the charges squared, and we have a constant here, and that's K. This is Coulomb's constant. Coulomb's constant is 9 times 10 to the 9th newtons meters squared per coulombs squared. Okay, so that's Coulomb's constant. Now, you know what a newton is. You know what a meter is. What is a coulomb? A coulomb is named after the physicist. And this is a unit of charge. Okay? 1 coulomb is actually a lot of charge. 1 coulomb is a lot of charge. To give you an idea, the charge of 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. It's negative, so it's a negative charge. The charge of a proton is positive 1.6 times 10 to the negative 19 coulombs. So it's a very small number of coulombs, the charge of a single proton or electron. And actually has it in the textbook here that it would take 6.25 times 10 to the 18 electrons or protons to have enough charge for 1 coulomb of charge. So 1 coulomb of charge is a lot of charge. So the definition of a coulomb. So that 1 coulomb is kind of defined by convenience, but this is the amount of charge in coulombs of an electron or a proton. So this is the fundamental amount of charge. So charge exists in multiples of this number, negative or positive. If you have a proton and if you have 1 electron and 1 proton together, they cancel each other out. If you had 2 electrons, you'd have a charge of negative 2 times 1.6 times 10 to the negative 19. So negative 3.2 times 10 to the negative 19. So all charge in the universe exists as integer multiples of this number, right? Either positive or negative, because that's the charge of 1 proton or 1 electron, positive or negative. So that's what a coulomb is. It's the unit of charge we use. And this is Coulomb's constant in this electric force equation. So if we have 2 charges, Q1 and Q2, and there's a distance r between them, the force that exists between those charges is calculated using this equation, where this is the charge 1, this is the charge 2, this is the distance between them squared, and this is Coulomb's constant. Now, unlike the gravitational force, which is always attractive, the electric force can be attractive or repulsive. If Q1 and Q2 are like charges, then the force is repulsive. It doesn't matter if they're both negative or both positive, they'll repel each other. If Q1 and Q2 are opposite charges, that same force, the same magnitude, but attractive. They will attract each other. So if you would increase the distance between the charge, the force that they exert on each other drops off with 1 over the distance squared. If you change the amount of charge, if you double the charge of one of these, or you would double the force on both. Okay. So the electric force on 2 charges is proportional to the product of the 2 charges and inversely proportional to the distance between them squared. So that is the electric force. Okay. And so this is the force that two charged objects, they bring them in contact with each other. This is how we calculate the force that they exert on each other. And we have to, there's no mathematical way to determine if it's attractive or repulsive. We just have to manually look. Are they the same charge or the opposite charges? So this brings us now to the electric field. So if we have a charge Q, capital Q, I'm going to call that charge, it creates an electric field around it. And the electric field is defined, the electric field, it's an E field, is defined by the force that the charge would exert on some test charge, Q. So if this is a charge Q here, if we put a little tiny test charge Q here, the electric field strength at this point is equal to the force that this charge would exert on that little test charge, okay, per charge. So let's see how this works out. So the force is K, capital Q, little q, over r squared, where r is the distance between them squared. So that's the force divided by the charge, so it's the force per test charge. And so the field strength, the electric field strength set up by some charge capital Q is equal to Coulomb's constant times that charge by 1 over the distance squared. So that's the strength of the field. So now we know the magnitude of the strength of the field set up by a charge capital Q located at some point R. It's equal to this. So if you increase this amount of charge here, you're going to increase the field strength. If you change R, you're going to change the field strength. So the field strength gets stronger as you get closer to the charge, because R gets smaller. The field strength gets weaker as you get further from the charge, because R gets larger. Now what direction? Now we always assume that little q is positive when working with electric fields. So if q is positive, and if little q, capital Q is positive charge, little q is positive charge, that's going to be a repulsive force. So if we make this, I'm gonna say red is positive. If Q is a positive charge, then little q is always going to be a positive charge. Then the force, electric force that Q exerts on little q is going to be repulsive. So it's going to be in that direction. And no matter where we put Q, if we put Q here, 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 wherever we put little q, the test charge, the force is going to be outward. And you'll notice that the further I am from Q, say over here, the weaker the force is, because it's further away. R is bigger. So the force that this positive charge, capital Q, exerts on some test charge, little q, anywhere, is going to be radially outward from the charge, and it's going to get weaker as you go further away from the charge. So this is the field strength. You can see the field strength gets weaker because it is a force field, right? The electric force field. It gets weaker as you go further from the charge that's setting up the field. We say that this charge is setting up this electric field, and it's out, away from the charge. Okay. Let me write this. We'll write this over here. The electric field is equal to KQ over R squared. Now, what happens if Q is negative? Now, if we put a little test charge Q here, the electric force is now going to be, remember the test charge is always positive. You assume it's always positive. It's going to be toward it because it's attractive. So, as we go further away from Q, the force is weaker because R is larger, but it always points directly in toward the negative charge Q that's now setting up the electric field. So the force due to the electric field set up by a negative charge always points towards the charge. The force from the electric field set up by a positive charge always points away from the charge. And so it's hard to draw these forces. So a force is a vector, has both a magnitude and a direction, right? So what we do with electric fields is we draw what are called field lines. Okay? So electric field lines are a graphical way of representing the electric field. It tells us what direction the force would be and how strong the force is. So if we have a positive charge Q, we can draw the field lines as radiating directly outward, and we put a little arrow indicating the direction. We can draw as many field lines as we want. The field lines tell us that if we put a positive charge in here, right, which direction would the force that this charge exerts on it be in? Well, if we put a charge in here, we can imagine the field line would be this way. It would push it this way, outward. And the strength of the force is illustrated by the distance between the field lines. The closer field lines are together, the stronger the force. So as you see, as you go further away, the field lines are further apart. So the weaker the force. And so the field is weaker. So the direction of the field line, so the force is always going to be tangent to the line at a point. Okay? And the strength is illustrated by the distance between. Now, if this was a negative charge, the field would look the exact same, except that they would point inward, because the force on a positive charge would be in toward the negative charge. So the field lines, so electric field lines, they move away from positive charge and they move in towards negative charge. Well, what happens if we have multiple charges present at the same time? Let's say we have okay. Well, if we put a positive charge, say right in the middle, say this is the same amount of charge, just positive or negative. Well, this is going to push the charge away, and this is going to pull the charge toward it. So, this is the field line. And if it was So note that all the field lines are pointing away from the positive and toward the negative charge. So that means if we put a positive charge here, the force, the force would be in this direction. It would be in this direction. Here, it would be in this direction. Here, it would be in that direction. It's always tangent to the field. So, if an object test charge right there, the force would be in this direction. And so the force is the strongest, the electric field is the strongest here, where the distance between the electric field lines is strongest. So I tried to draw them equally spaced, radiating from each charge. You can see the electric field is weakest over here and over here, and it gets even weaker as you go further away. And so this is where the electric field is the strongest because the field lines are the closest. So if you put a test charge in here, you're going to experience the largest force in here. And that test charge would be pushed in this direction and then apply the positive charge and pulled in this direction by the negative charge. What if we made put two light charges next to each other? Well, it's easy on this side, right? These just push positive charges away that way. But here, this would push the positive charge that way, and this would push the positive charge that way, and it would cancel out. And so the strength of the field is actually zero. If these are the same charge at the midpoint, the field strength is actually zero. Right? Because the forces will cancel each other out. Because remember, the field strength is the force divided by Q, right here. This is the field due to one charge, right? Q. If you have to add up the fields due to multiple charge, so the total electric field would be the electric field at this point, and the electric field is a vector, so one of these would be positive, one of these would be negative, and they cancel each other out at that point. So how the electric field would actually look here. And if something was down here, both the force due to this charge, let's say up here, more space. The force due to this charge would be in that direction. The force due to that charge would be in that direction. And so this component cancels out of this force, cancels out that component, that force, so the net force would be in that direction. So that's the field line is going to be I'll draw it this way. No, those are too close. So this is what the field lines will look like for two positive charges. The electric field is actually zero here in the center, right? They're really spread apart because there's no force. The force is zero. So if we put a charge anywhere in here, these field lines tell us how those charges would exert, how those charges, but the force of those charges would fill the direction and strength, depending on how close the field lines are. So that's the concept of an electric field. Okay, so it tells us the field is equal to the force that the charge or charges exert on a test charge divided by that test charge itself. And so, because the electric field is the force divided by the test charge, the units of electric field are newtons per coulomb. How many newtons of force per coulomb charge are exerted on that charge? So if you had a field strength of 1, that means that for every 1 coulomb, say the electric field strength is equal to 1 newton per coulomb at a particular place, then if there's 1 coulomb charge, which is a lot of charge, there would be 1 newton of force exerted on it. Right? So that's the units of an electric field. So next we have electric potential. So this is just like gravitational potential. If we want to move something, say this is the surface of the Earth, from here, h equals 0, to some h, we're going to exert a force, F, equal to its weight, mg, upward, a distance of h. So the work we have to do against the gravitational field to move an object from the surface of the Earth to a height h, work is force through a distance. The force is mg, the distance is h, so the work we have to do against gravity is equal to mgh. And the work that we had to do against gravity, gravity can give that work back. If we let it go, it will exert a force mg back through that distance. And so by doing work against a conservative force like gravity, we add potential energy to the object. In this case, gravitational potential energy. So the same thing is true for electric forces, right? If we do work against the electric force, that means there's potential energy now stored. So the electric force, so let me write it this way. If there is an electric field, right, goes like this, right? Now, if we have a charge, say positive charge Q, if we want to move it from here to here, we've got to exert a force on it to move it through that field, because this field wants to exert a force on it that way. So we've got to exert a force on it this way. And so, remember, the field is force over Q. So the force, if this has a field strength E in this direction, the force we've got to exert on it is the field strength times Q. That gives us the force. Field strength times Q gives us the force. That's the force you're going to exert on this little charge Q to move it through this electric field. Now, if we move it a distance, say x, that's now the electric potential energy. Electric potential energy we have added to this object. That means if we would let this object go, that electric potential energy could be converted into kinetic energy, and it would accelerate and speed up and have a kinetic energy at this point. So just like if you lift something in Earth's gravitational field, you do work against the gravitational field. If you let go of it, that gravitational field stores, as you do work against the gravitational field, you're adding potential energy to the object. If you let go of it, the force field, the gravitational force field, will do work on the object and increase its kinetic energy. So that's potential energy. The same is true with the electric force. If you do work on a charge against an electric field, you're adding electric potential energy to it. If you let go of it, then that electric potential energy will be converted into kinetic energy. The charge will accelerate and it'll develop a velocity. You'll have a kinetic energy here equal to its potential energy there. So if you do work against a electric field, you're adding electric potential energy, which has units of joules. So it's force Newton meters. Force through a distance. Now I drew that force field with parallel lines. How do you create that? One way to create that is if you have a plate that has a positive charge on it. And then if you have a plate that has negative charge on it. Okay? Be like a capacitor. And here in the center, the field lines, they're straight across. At the edges, well, no, the field lines at the edges, they might stray a little bit. But in between those plates, the field lines are straight across. So that's how you can create a uniform electric field, is by like, two plates that have opposite charge. So if you put a charge, here, positive charge there, the force you have to exert on it, this direction to move it from here to here, is equal to, this has an electric field strength of E. E times Q is the force that the exert on this charge to move it through the field. And this distance, let's call this distance x. E, Q, x, that's the work you have to do to move from there to there. And so this Q over here, it doesn't want to be over here. It doesn't want to be this close to the positive charge. It's attracted to the negative charge and repelled by the positive charge. So it has potential energy. That potential energy is equal to EQ times this distance, x. So that's the electric potential energy. It has units of joules. Newtons times meter is a joule. So that's electric potential. Okay? Now, if we look at the electric potential energy per divided by a little charge Q, that gives us the electric potential energy per charge, per coulomb. And we give this, so this would have units of joules per coulomb. This is how we define electric potential. Potential. This is different than sorry, I talked about electric potential energy. This is different than electric potential energy. Electric potential is the electric potential energy per charge, per coulomb. And we call that the volt. A volt is a unit of electric potential, and it is the amount of joules of energy, potential energy per coulomb. So let's say the voltage across here is 12 volts. What does that mean? That means if you had 1 coulomb, that means there's 12 across here. There's 12 joules of energy, potential energy per coulomb. So if you put a coulomb of charge here, say positive charge, and you let go of it, by the time that charge got there, it will have gained that 12 joules of potential energy will be converted to kinetic energy of 12 joules. So it has 12 joules of potential energy per coulomb charge from here to there. Likewise, if it was a negative charge, it would have 12 joules of potential energy, and by the time it got here, it would have 12 joules of kinetic energy. So volts is the amount of potential energy per coulomb of charge. And so the larger the voltage, the more potential energy, right? The more potential, the more that the electrons can be, or the protons can be excited, can be sped up. And so if you have more, just like if the larger the potential is, the more kinetic energy an object will have, and once that potential is converted to kinetic, the same thing is here. So if you have, say, a 20 volt battery, then that means that that battery can give 20 joules of energy per coulomb charge, to 1 coulomb charge. Now if you think, say you look at one electron has charge of 1.6 times 10 to the negative 19 coulombs. So if we have a 12 volt battery, how much energy how much potential energy can be converted to kinetic energy for one electron? Well, 12 volts is 12 joules per coulomb multiplied by, well, an electron has 1.6 times 10 to the negative 19. That's how much charge is in an electron. So I multiply this by 12, 1.6 times 10 to the negative 19 by 12. I'll use this calculator here. .6 times 10 to the negative 19 times 12. We can give one electron 1.92 times 10 to the negative 18 joules of energy. Right? So we could, that's how much energy a 12 volt battery can give to one electron. So this is the voltage is the joules of energy per coulomb. So it's the amount of potential energy per coulomb that can be delivered. So the larger the voltage, the more energy per coulomb that can be given to the charge. And so, say a 24 volt battery would give an electron double the amount of energy. And so, in order for electrons to move, say, in a circuit, they have to move, they have to have energy, kinetic energy. And the larger the voltage of the battery in the circuit, so the battery is the potential energy that drives the circuit, drives the electricity in the circuit. So the larger the voltage in the battery, the more energy can be given to the electrons and move them faster. So the larger the voltage in the circuit, larger the voltage of the battery, the faster the electrons can move in the circuit. Okay, because it's more joules of energy per coulomb charge. You can think about it this way: you can give a single charge more energy, or you can give the same amount of energy to more charge. You can move more charge, give more charge, the same amount of energy. So that is electric potential voltage. It's volts, joules per coulomb. And that concludes the lecture on electricity. And our next lecture will be the final one for the course, which will look at electric current.